Have you ever wondered what the world around you is made of? Buildings, roads, bridges. Most of them are made of concrete. But its main ingredient, Portland cement, is responsible for about 5% of global CO2 emissions, making it one of the most polluting materials on the planet. In the face of this problem, we are looking for more sustainable solutions, replacing part of the cement with materials like fly ash, blast furnace slag, and silica fume. We analyze a base mix and two alternatives to reach a final dosage, evaluating its durability and environmental impact. The result shows that it is possible to build in a responsible and resilient way.
Let's start with the materials obtained for the base case. Portland cement was sourced in Guayaquil, meeting the ASTM C150 and chosen for its nearby location. We used 832 kilograms of natural stones that represent 58% of aggregates, transported about 13 kilometers by road. Also, 953 kilograms of natural sand and represent about 27% was used. Transported 14 kilometers, where it came from the laboratory, no transport needed. All materials with road transport. For the base mix, we use a water to cement ratio of the 40%, ensuring the good strength and durability of the concrete. The simulation was carried out considering a plant located on Espol. Regarding the composition, the coarse aggregate representing the 53% of the total aggregate mass, exceeding the minimum requirement of the 30%.
For the alternative case, cement, aggregates, and water were obtained from the same suppliers used in the base case, so the transport distances remained the same. As for the supplementary cementing materials, they cover fixed distances and use different transport methods. Blast furnace slag travels 20 km by road and 250 km by river. Fly ash travels 100 km by road and 200 km by train. Silica fume travels 50 km by road and 200 km by train. These distances directly influence the environmental impact of transporting each material. Remember that for the alternative case, two dosages were performed. Both dosages use 255 kg of cement, 832 kg of sand, 953 kg of stone, and 150 kg of water. Only the proportion of steams varied.
In the first dosage, we performed 11 iterations varying the SCMs. We used the Live 365 software to simulate marine environments in Guayaquil. The base case showed a useful life of 11.92 years. This combination allowed an improvement in durability thanks to the action of the silica fume, which react with the calcium hydroxide produced during cement hydration. This former calcium silica hydrate densified the concrete's microstructure and increasing its resistance to aggressive agents. As seen in the graph, by increasing the silica fume percentage, the concrete's useful life reached up to 106 years. The result represents an improvement over the base case. In the second dosage, we used 30 and 40% fly ash with GGBS and silica fume from 10 to 0%, seeking a balance between durability and environmental impact. The best environmental performance was achieved by replacing 40% of the cement only with fly ash, due to its low carbon dioxide emission. The longest useful life, but with less reduction in environmental impact, was achieved with 30% fly ash, 0% slag, and 10% silica fume, showing the high impact of silica fume. On the other hand, with 30% fly ash and 10% GGBS, the shortest useful life was achieved, but with a greater reduction in environmental impact, reinforcing the negative effect of silica fume in ecological terms.
We decided not to use silica fume, despite improving durability, has the highest carbon dioxide emission among SCMs. GGBS, on the other hand, reduced the service life of the concrete in our analysis, is unlocally available, and has higher carbon footprint than fly ash.
Based on the results of the base phase, in this dosage we replaced 40% of Portland cement only with fly ash, as it showed good performance without increasing environmental impact. The same amounts of water and aggregates were kept as in the base case. The only difference was the use of 60% cement and 40% fly ash as the cementing material. This mix achieved a useful life of 23.61 years, almost double that of the base case, which was 11.92 years. This is equivalent to a 1.99 times improvement in durability in marine conditions. To evaluate environmental impact, we perform a life cycle analysis, LCA, considering the extraction, production, transport, and distribution stages of the materials. These phases were crucial because they represent the largest contributions to console emissions in the concrete chain, from raw material extraction to delivery on site. Additionally, when evaluating the 5 categories of environmental impact, the alternative case showed an average reduction of 18.1% in emissions compared to the base case.
An 18.1% environmental impact reduction was achieved based on 5 key categories. The most significant improvements were global warming, 31.3%, fossil fuel depletion, 26.6%, and ozone depletion, 25.2%. However, for toxicity and carcinogenicity showing minimal reductions, 6.2% and 1% respectively. These low scores are mainly due to the continued use of Portland cement, which is highly polluting and difficult to replace. The GGBS was avoided due to the low impact and silica fumed due to the cancer risk, but silica remains present in cement-based materials. The improvements were made possible by replacing 40% of Portland cement with coal fly ash, cutting emissions and fossil fuel use. Over the results, 18.1% impact reductions and a 1.99% service life score highlight the potential of sustainable strategies, while also showing there's more to be done, especially in reducing the effects of traditional materials.